Dear students, welcome to the third part of NMR Spectroscopy. In this video, we will have a detailed discussion on the splitting of signals in NMR spectrum and also about the relative intensity of peaks. We have seen that each signal in an NMR spectrum represents a particular set of equivalent protons, chemically equivalent protons in the molecule. And the number of signals will be equal to the number of equivalent set of protons. For example, if we consider the case of acetone, CH3COCH3, similarly benzene, tetramethylsilane, which is a standard used in NMR. In all these molecules, all the protons are in identical chemical environment, or we say that all the protons are chemically equivalent, and hence all these set of protons will give a single peak in the NMR spectrum. That is, they will give only one NMR signal. If there are two different set of chemically equivalent protons, then such molecules will give two NMR signals. If we consider ethyl bromide CH3CH2Br, there are two different sets of protons. One is the CH3 protons, which is attached to CH2Br, and the other is CH2 protons. This is attached to a CH3 group and a bromine atom. So the two type of protons, the CH3 protons and CH2 protons, are in different chemical environment, and hence ethyl bromide will give two NMR signals. So we expect two peaks in the NMR spectrum of ethyl bromide. But if we take a closer look into the NMR spectrum, we can see that in certain molecules, instead of a single peak, multiple sets of peaks are observed. Here you can see the spectrum of ethyl bromide. As I said earlier, there are two different sets of chemically equivalent protons. So we expect two peaks in the NMR spectrum. But if you look at the NMR spectrum of ethyl bromide, you can see that each of such peak is split into different lines. For example, the peak due to CH3 protons, which is shown in blue color here, there are three lines instead of a single peak. Similarly, the peak due to CH2 protons, which is shown in green color, we can see four different lines. So instead of two single peaks, here we can observe peaks which are split into different lines. So this phenomena of splitting of lines into groups of two or more component peaks is called spin-spin splitting. Normally we expect single peaks corresponding to the number of equivalent set of protons, but the actual spectrum will contain peaks which are split into different components. So such splitting of peaks into groups of two or more component peaks or component lines is called spin-spin splitting. Now let's see why such splitting of lines occur in an NMR spectrum. The splitting of lines in an NMR spectrum is due to the coupling of spins of the neighbouring protons, which is transmitted through the bonding electrons. And this is known as spin-spin coupling. So let's see what is meant by the coupling of spins or spin-spin coupling. We know that both protons and electrons are charged particles. Protons are positively charged, whereas electrons are negatively charged. Again, Both possess spinning property. So any charged spinning particle will generate a magnetic field, that is, it behaves as a tiny spinning magnet and creates its own magnetic field. So both proton and electron have spin, and since both are charged particles, they can generate a magnetic field of their own. So consider two protons A and B, which is connected through bonding electrons. So here you can see the spin of proton A, and this is the spin of proton B, and these two protons are connected through bonding electrons. So a bonding electron will have a tendency to pair its spin with the spin of the nearest proton. The spin of the electron is affected by the spin of the neighbouring proton. So this will affect the spin of another bonding electron, which is then transmitted to the spin of the next proton. That means there occurs an indirect spin interaction between proton A and proton B, and that is taking place through the bonding electrons. So this indirect spin interaction between the neighbouring protons taking place through the bonding electrons is called spin-spin coupling. It is due to this spin-spin coupling that the splitting of signals occur in an NMR spectrum. So the splitting of signals in an NMR spectrum is due to the coupling of spins of the neighbouring protons, which is transmitted through the bonding electrons. This is an indirect interaction between the spins of the neighbouring protons. Why it is called indirect? Because this interaction is occurring or transmitting through the intervening bonding electrons. The spin of one proton, say proton A, will be interacting with the spin of one bonding electron, which is then transmitted to the other bonding electron, which will then be transmitted to the next nearest proton, say proton B. So in this way, an indirect spin-spin interaction occurs through the intervening bonding electrons, and such an interaction is called spin-spin coupling. And it is due to this spin-spin coupling that the splitting of signals in an NMR spectrum occurs. The magnitude of spin-spin coupling depends on the number of bonds between the nuclei involved. If the coupling is transmitted through two bonds, as it is shown here, it is called geminal coupling. The spin of the proton on the left is transmitted through these two bonds and will interact with the spin of proton shown on the right. So such a coupling is called geminal coupling. And if the coupling is transmitted through three bonds, then it is called vicinal coupling. And generally, splitting is not observed between protons separated by more than three bonds. So we have seen that spin-spin coupling causes the splitting of lines in the NMR spectrum into multiplets or different number of lines. And the number of multiplets or number of lines in a group will depend on the number of protons in the adjacent group. So based on that, we will see some general rules for determining the multiplicity of a signal. The first rule is chemically equivalent protons do not give rise to splitting. Chemically equivalent means protons in identical chemical environment or protons with the same chemical shift value. They do not give rise to splitting. That means there will not be any splitting from the coupling between the protons attached to the same carbon if they are equivalent. Similarly, consider CH2Cl, CH2Cl. Here we have protons on one carbon and protons on the second carbon. These two sets of protons are equivalent, and hence, though these protons are on different carbon atoms, they do not undergo spin-spin coupling because they are chemically equivalent. Now, an H1 NMR signal, that is a proton NMR signal, is split into n plus 1 peaks where n is the number of equivalent protons bonded to adjacent carbons. And this is generally referred to as the n plus 1 rule for proton NMR spectroscopy. Now let's see one example. Consider the splitting of the CH proton, that is the proton marked in red. If we are considering this proton, there will be spin-spin coupling between this proton and the proton on the adjacent carbon. So that means there will be interaction between the spins of CH3 protons and this CH proton. So what will be the number of lines in the NMR peak of CH proton? So according to the rule, a signal will be split into n plus 1 peaks, where n is the number of equivalent protons on the adjacent carbon. So on the adjacent carbon, we have CH3, that means 3 protons. So according to n plus 1 rule, it is 3 plus 1 equal to 4. That is, the signal due to CH proton will be appearing as a quartet. A quartet means 4 lines. As you can see here, this is a quartet. Now, what will be the number of lines in the peak due to CH3 protons? So, on the adjacent carbon, we have only one single proton. So, the number of peaks will be n plus 1, that is 1 plus 1 is equal to 2. So, the peak due to CH3 protons will be split into 2 lines, that is, it will be appearing as a doublet. Doublet means 2 lines. So, this is how the splitting of peak occur in an NMR spectrum. A signal in an NMR spectrum, proton NMR spectrum, will split into n plus 1 peaks, where n is the number of equivalent protons bonded to adjacent carbons. So like quartet or doublet, we can see different kinds of peaks like triplet, quintet, etc. Now, when 2 sets of adjacent protons are different from each other, that is, if we have n protons on one adjacent carbon and m protons on the other, then the number of peaks in an NMR signal will be equal to n plus 1 into m plus 1. So consider this example, CH3, CH2, CH2, Br. The CH3 protons are marked HA, the CH2 protons are marked HB, and the next CH2 proton attached to bromine is marked HC. Now consider the middle set of protons, that is the middle CH2 proton marked as HB. Now we have to find out what will be the number of lines in the peak due to this middle CH2 proton. So we can see that on one side we have a CH3 proton and on the other side we have a CH2 proton attached to bromine. So according to the rule, if we have n protons on one adjacent carbon and m protons on the other, then the number of peaks will be n plus 1 into m plus 1. On the left side we have CH3. So 3 HA protons will split the peak of CH2 proton, the middle CH2 proton, into 3 plus 1, that is n plus 1 equal to 3 plus 1 equals 4. And on the right side we have a CH2 attached to Br. So number of protons is 2. So the splitting of peak will be 2 plus 1 equal to 3. So n plus 1 into m plus 1, that is 4 into 3 equal to 12. So that is shown here. We'll have 12 lines in the peak due to this middle CH2 proton, and that is appearing as a quartet of triplets. 4 set, each set containing 3 each lines. So if there are only one set of protons on the adjacent carbon, then the number of peaks will be n plus 1. If you have different sets of protons on both sides, then the rule will be n plus 1 into m plus 1. We have seen that in an NMR spectrum, there will be multiple sets of lines or multiplets like doublet, triplet, quartet, etc. So what will be the intensity of these lines? The relative intensities of a multiplet will be symmetric about the midpoint, and it is proportional to the coefficients of the binomial expansion 1 plus x raised to n, where n is the number of equivalent protons that interact with a specific proton. And those coefficients are given by the famous Pascal's triangle. That is as shown here. This is the Pascal's triangle. If n equals 0, we will have a single peak and the intensity is 1. If n equals 1, then the peak will split into 2, that is it will be a doublet with intensity ratio 1:1. So by looking at the Pascal's triangle, we can easily say the intensity, this it is 1:1. If n equal to 2, then the peak will split into 3 lines, that is a triplet, and the intensity will be 1:2:1. Similarly, if n equals 3, it will be a quartet with intensity ratio 1:3:3:1. So by looking at the Pascal's triangle, we can easily predict the intensity of lines, multiplets in an NMR spectrum. Also, the midpoint of the multiplet represents the resonance position of a group and thus gives the chemical shift. Once again, let's look into the NMR spectrum of ethyl bromide. In ethyl bromide, as I said earlier, there are two different sets of equivalent protons. The CH3 protons is one set and the CH2 protons is another set. So definitely we will get two NMR signals in the spectrum. But we have seen that each of that signal is split into different lines due to spin-spin coupling. We know that the spin of the CH3 proton will couple with the spin of the neighbouring CH2 proton, and according to n plus 1 rule, what will be the number of lines in the peak adjacent to CH3? We have CH2, that is 2 protons. So according to n plus 1 rule, we have 2 plus 1 equal to 3. So 3 lines in the peak due to CH3 protons. So that is indicated in blue here. You can see 3 blue lines. It's an upfield peak. It's about 1.7 ppm due to CH3 protons. And this is appearing as a triplet due to its coupling with the CH2 protons. Now what will be the number of lines in the peak due to CH2 proton? Again, there will be spin-spin interaction between the neighbouring protons. So adjacent to CH2 is the CH3 proton. So n equals 3, therefore 3 plus 1 equal to 4, and that is shown as green lines here. It is a quartet. It's a downfield peak at about 3.5 ppm, and this is due to the CH2 protons. Why delta value is higher? Because it is this CH2 proton is also de-shielded by the electronegative bromine atom, and due to its coupling with the neighbouring CH3 proton, the peak appear as a quartet, that is with 4 lines. So this is about the NMR spectrum of ethyl bromide. Now let's see how we can actually explain the relative intensities of peaks observed in the spectrum. We have seen that the splitting of signals occurs due to indirect interaction of the spins of the neighbouring protons. We consider the case of CH3 proton. Adjacent to CH3 we have a CH2. So number of protons is 2. The spin of these 2 protons can be oriented as shown here on the left side. This shows the direction of the external magnetic field. So either the spin of the 2 protons can be parallel and aligned with the field. That is both up, or the two spins are again parallel but aligned opposite to the field. That is two spins are down but they are parallel, or it can be one up and one down. So likewise there are two probable combinations. That is the spins are opposed to one another. Thus the peak due to CH3 protons will be split into three equally spaced peaks due to its coupling with the CH2 proton. And why three equally spaced peaks? Because of the possible orientations of the spin of the neighbouring proton. And who is the neighbour of CH3 protons? It is the CH2 proton. Number of protons is 2. So the two protons can be arranged in this fashion, and as a result the CH3 signal is split into three equally spaced peaks. That is, we will get a triplet with relative intensities of 1:2:1. And why in this ratio? Because the orientation in which the spins are opposed to each other have two probable combinations, either one up and one down. So the relative intensity will also be in the ratio 1:2:1. Okay. Now let's see about the signal due to CH2 protons. So the signal due to CH2 protons will be affected by the number of neighbouring protons, and the neighbour of CH2 is CH3. So N equals 3. So we have 3 protons. These 3 protons, the spin of these 3 protons will be arranged in this fashion. Either the spin of 3 protons are parallel and aligned with the field, or they will be parallel but aligned against the field, and then it can be either 2 up and 1 down. Likewise, there can be 3 probable combinations. Similarly, 1 up and 2 down. Likewise also there will be 3 probable combinations. So that means the signal will be split into 4 lines. That is, it will be a quartet, and the relative intensity will be 1:3:3:1. Since there are 3 probable combinations of 2 up and 1 down and 1 up and 2 down, the intensity ratio will also be like this, that is 1:3:3:1. So we can say that the number of lines in a signal of a specific proton and its relative peak intensities will depend upon the number of equivalent protons on the adjacent carbon atoms. The splitting as well as the relative intensity depend upon the orientation of spins of the adjacent equivalent protons. So we can say that the NMR spectrum of ethyl bromide contains 2 peaks, a 3 proton triplet for the CH3 protons due to their coupling with the CH2 protons, and also a 2 proton quartet for the CH2 protons due to their coupling with the CH3 protons. In a similar way, we can explain the spectra of other compounds also. The next is coupling constant. We have seen that each signal will split up into multiplets. The spacing between adjacent lines in a multiplet is known as coupling constant, usually represented as J, and it is measured in Hertz. This coupling constant is the direct measure of the spin-spin coupling. That is, it is a measure of how strongly a nucleus or a proton is affected by the spin orientation of its neighbouring proton. However, J values are independent of the applied field strength. So here you can see a quartet. So the spacing between the adjacent lines, these two lines, or the distance between these two lines. Okay, the spacing between the adjacent lines in this multiplet is known as the coupling constant, represented as G.